So, I'm suggesting here a new paradigm to assess the effectiveness of upbeat group control algorithms. Paradigm is an emotive word. It's, we're really sort of saying it's a new way of thinking. I hope you will agree it is a new way of thinking. Let's see whether you agree or not. So, upbeat group control algorithms include obviously the sectoring, and they include destination in one of its formats. So I'm going to talk about introduction and motivation. Why are we doing this? And I'm going to give you some analogies. We all like analogies when we're explaining things and so on, so I'm going to try to give some analogies. And the analogy I'm giving is about how we assess candidates. Three pillars of this new paradigm. And I'm going to be talking about TLAs. Anyone knows what TLAs are other than Richard? Three-letter acronyms. Talk about some initial results and the advantages. So, the old hairy chestnut of elevated traffic design. A cake and a coffee. I'll buy a cake and a coffee. Who tells me what that is? What is the old hairy chestnut which we keep talking about when we talk about elevated traffic analysis, and there's arguments and so on? Come on, Len.
What are we talking about? Upbeat traffic?
Analysis, methods of analysis. And design.
Simulation.
Simulation, thank you. Yeah. A cake and a coffee, that's all I can offer you. So, that's one of the big debates I have with Richard. We always have, and it's not really a debate, but we keep on talking about, is it calculation, is it simulation? Is calculation old hat now? And you move on to simulation. And obviously the nice compromise we always find to keep everything happy, we say, well, it's actually a bit of both, isn't it? It's the old cliche, each one has its strength. So traditionally, simulation has always been used for assessing a group control algorithm. It has many advantages, of course. It can deal with situations get very, very complex, and then you really have to move to simulation. You can't carry on doing calculations, coming up with formula. It does suffer, however, from a number of advantages, and obviously some of that was evident yesterday in the second workshop. I think it suffers from the problem of repeatability, and some people will correct me on that and say, if you repeat this a number of times, you will get the result. Okay, that's fine. But I think it is debatable whether it is repeatable or not. When we talk about measurement systems, the two terms that always come up, precision, repeatability and reproducibility. And my argument is that repeatability is something that you keep on getting the same result by the same user, by the same designer, by the same assessor. Reproducibility is something that you're getting the same result, reproducing the same results by others. I don't know whether Stefan agrees with that, but that's my take on that. Transparency. It is very opaque, and objectivity. So we are looking for an assessment tool. I'm looking for an assessment tool. I believe that a good assessment tool will have those features. It has to be transparent. You have to understand what's inside it. Now, you can argue that it's impossible to do that, but at least we must have some understanding of how it's working. It has to be repeatable, reproducible. I've got a very interesting example on reproducibility. I've got a cautionary tale to talk about reproducibility at the end of this presentation today. I think you'll find it very interesting. And it has to be objective. So let's have a look at analogies. I love analogies. They're an absolutely fantastic way of clarifying things. The students love them, you love them too. I think we've got two analogies today, or three in fact. I've added one for the benefit of the LFCon attendees. When you assess a candidate, you want to have an all-rounded candidate, don't you? I don't know, if Stefan brings in a lecturer, I'm sure he wants to know that that lecturer is good on research and he's good on lecturing and he's got good interpersonal skills and doesn't give him problems and so on. He's a good team worker. I'm sure that's another. So it would be wrong for you to take someone and assess them on just one point and say this guy is great. He's a great, for example, lecturer, or he's a great researcher, and then he's poor on other sides. You would want to assess them on everything, and that's what we want to do with a group control algorithm. A group control algorithm might be excellent under one scenario or one situation and very poor under the others. And we do that when we assess candidates. We ask them questions, we put them under psychometric tests, and this is an example. An office with a view, vegetarian options at even 72 degrees. And the guy said references, not preferences. That's another example about good people skills. Yes, I think I have good people skills. What kind of idiot's question is that? This looks like Stefan actually. Where's Stefan? Or is it Ingo? So, we're looking for some good engineering managers to recruit. We want to assess them objectively, want to make sure they're all well-rounded, and they can deal with different situations successfully. And it's exactly the same thing with a group control algorithm. You want to make sure you're testing that group of control. It doesn't fall down on one condition, under one condition or another. So we do aptitude tests, stressful situations, simulated reality, and so on. And then we have a weighted average, because you might not think that all of these features are equally important. So you give one of them more of a weight, and you give one of them less of a weight. And you say, for example, I'm going to give 50% to team working, 5% to report writing, and so on. Now, the technique will have 3 pillars. What I'm suggesting, the new paradigm has 3 pillars. And each one of them, the first one, for example, is I'm talking about random scenario testing. So we're generating these random scenarios. I like Monte Carlo simulation. Monte Carlo simulation is a great way of generating randomly different scenarios. So we're going to expose the group control algorithm to randomly to different scenarios. And these scenarios will be generated randomly, and every time we see how it performs under that scenario. We just take one scenario at a time and throw it away. We take another scenario, while simulation carries on continuously, doesn't it? Simulation will start and carries on continuously. We're taking a scenario at a time and then evaluating it. So we randomly generate a scenario. Then we see how the group control algorithm allocates those cars to the, allocates the calls to the cars. And it has to perform in that scenario. Then we assess its performance under that scenario. It could use rules. Now the tool doesn't matter. Tools are a completely different thing. We sometimes get confused between a tool and an objective. We have to understand what we do first. Rather than say, I've got this very nice chainsaw, what can I do with it? And as engineers, that's what we do sometimes. We say, I've got this fantastic tool, how can I use it? What we should be saying is, what is my objective? And then I can think, what tools do I need? And we can use rules, heuristics, optimization techniques. Simulation by its very nature is continuous. This method is quite discrete. It's taking one scenario at a time, and then it's using it to assess. If you put this on silent, it doesn't stop the alarms. That's the problem, isn't it? So, nothing is carried out over from one scenario to the next. We actually throw everything away and we start again. And this is an example. This is an example where you have lifts continuously running around the building, and that's continuous in nature. But in our case, we actually generate one scenario at a time. So, we generate a scenario, we solve it, we generate a second scenario and solve it. We carry on doing that for 10,000, 10 million times, and then we take the average value. And that's actually a representation of the method. So this is called random scenario testing. You can then solve it any method you want, analytical methods, graphical methods, numerical methods, it doesn't really matter. The second one is what I've called an idealized optimal benchmark. And we use idealized optimal benchmarks in life. This is a book I read around a couple of years ago. Some books really shake you. You really sit there and think, like a film, you watch a film and it shakes you, it makes you think about lots of things. That's what a good book is about, isn't it? This is an excellent book. I think it's by Ian Stewart. I think he's from Coventry University, a professor of mathematics, but he loves popular science, so he does these books about popular science. And he compiled the most important 17 equations that he believed changed the world. One of them was about the second law of thermodynamics. And when I read this, I was fascinated. I'm not a mechanical engineer, I'm an electrical engineer. Those of you mechanical engineers in the audience will remember that this is actually looking at a thermal engine, a heat engine, and then saying that's the maximum limit of efficiency that you can achieve. You can't go above it. So we have a heat engine. This is a device that can convert thermal energy into mechanical energy. Steam engine is an example. We have a hot source of temperature. That's a source of heat. And then we have a heat sink. And basically we're saying that we have a source of heat here at a certain high temperature. We have a sink. And as the heat is flowing from the hot source to the cold source, we can convert some of that into work, useful mechanical work. But you can't convert all of it. No matter how good that machine is, even if it's the best machine ever, there's a limit, there's a theoretical limit. And it's very clever that someone came up and said that is a theoretical limit. You can't, no matter how good you are, how good your machine is, even if it's perfect machine here, that efficiency can't be 100%. It has a limit. And there's a formula for what that limit is. So don't waste your time and try improving that machine, that steam engine, over and over again. There is actually a natural limit. Now that's a very interesting concept. It's saying to you, don't work very, very hard. You're not actually very far from the optimum. And knowing that is actually very useful. So what the equation basically is saying is that efficiency is equal to the hot temperature in Kelvin minus the low temperature. So it depends on the difference between the two temperatures divided by the hot temperature in Kelvin. So you find, for example, if you have a steam engine with a, I don't know, 140 degree heated steam and a room temperature of 25, the efficiency will not be more than 67, 66%. I don't know whether that's the right number. It's very, very informative because it's saying to you, that's your limit, that's the benchmark. You will never ever go above that, no matter how good the machine is. And that's very informative for group control algorithms. It tells you, I can then say that algorithm has improved, but it's actually only 2% away from the idealized optimal benchmark. Let's quickly have a look at this engine. How much time have we got? 25 minutes?
We're okay. Yeah.
Let's have a look at this video.
This is a stirring engine, one of those remarkable handheld ones which relies on only the heat of the hand. So the difference in temperature is merely the difference between my warm skin of my hand here and the top surface, which is the room temperature. And it only came out a few years ago because the technology is quite advanced. And
so basically you have there's the hot temperature, which is not very hot in this case. It's only 73 Celsius, maybe 300 and a bit Kelvin. That's the room temperature. And heat will start flowing from that hot plate up to the cold plate here, and in the process it's actually going to do some mechanical energy. I calculated this based on a very, very simple calculation, and the efficiency, the maximum possible efficiency of that is only 4%, which sounds very low, but it means that if you've achieved 3.5%, you've done very, very well. Don't beat yourself up. So let's just see it moving.
You've got to have very, very finely made materials. Isn't that amazing? It's already working on the heat of my hand. So the hand, my hand is providing heat for the bottom plate, which is warming the air, and that then pushes the piston up into the power piston here. And
okay, that's you've just got the idea, because I've got another example in an IOB. Now, the other equation, that's also an equation in the book, Shannon, Claude Shannon. Claude Shannon was an American mathematician, electronic engineer, very famous for his Shannon channel capacity theorem, 1948. And this was actually quite a landmark as well. It was a very, very important insight, because he actually could, it's also in that book in there, and he was giving us an upper bound as well. There's the word coming back again. He was giving us an upper bound on what is the channel capacity, how much data can I send down through a channel. All I need to know, and this is an important thing, is all I need to know is the bandwidth and the signal to noise ratio. If I knew those, then I can say the maximum data you can send through this will not exceed, for example, 1 kilobits per second or 1,000,000 kilobits per second. And that was very, very important, this principle. So once I see a system, this is why this is important, I can tell the upper performance limit of the system without the need to study the details of the system. I'm just taking a black box or a macroscopic view of the system on the outside. So I don't need to study the details of the system. I can just apply the equation and say from known parameters, and then say what the upper limit, the bound on that system is. So the same principle can be applied in a building that's being controlled using destination. That's the proposition. That's the hypothesis that I'm presenting here. By knowing some parameters in that building, without actually delving too much into the details of the algorithm, that's the important thing. We can actually assess the upper limit on the performance of that algorithm, and then we can start saying, I've achieved that much, and the upper bound says it's that much, so I'm doing reasonably well. So what I've assumed in here is we've taken a building with n floors. I'm working on the principle of sectoring, and those of you who design destination control systems, that's one possibility, it's not the only possibility. So we can have a destination control system, and we split the building into virtual sectors. So we're saying we will assign the calls in that sector to one lift, the calls in that sector, the calls in that sector to a third lift, and so on. And basically we split the building into virtual sectors. The destination passenger is unaware of this. It's all hidden from him or her. We're just doing that behind the scenes. And we're rotating those. We're rotating the elevator will go to sector 1 first, and this is a round robin. It's like a round robin, and then it goes to the second one, then it goes. So they go in a round robin fashion, very similar to when channeling first came out by Otis. They would do a round robin. They would actually rotate the lift to the different sectors. From this now, you can come up with two simple equations, an effective H and an effective S. This is the rotation of lifts to sectors. So this is the round robin rotation. So the first lift will go to the first sector first, second sector, third sector, fourth sector, and back again. And this equalizes the loading of the handling capacity of the different sectors. Now this is the equation. This is similar to the equation for the heat engine or the equation for Shannon. We just have a value for S, a value for H, and we go back to the well-loved equation, the round-trip time equation from Barney and Dos Santos in the 70s. Just apply S there, you plug in S, you plug in H, and you come up with a new round-trip time formula. The third one is progressive introduction of reality. And after I did the LFCON presentation, I had the word utopia. I didn't have the opposite word. Anyone knows what the opposite word of utopia is? Dystopia. So we're moving from the ideal situation, ideal utopia, and then gradually working our way to reality, passing reality and going, well, we're not going to go to dystopia, but we start from idealized conditions. We start calculation with the ideal optimal benchmark. We know that's not going to happen in practice. This is very, very hypothetical, but it's nice to know what it is. Then we start moving towards reality. So we have offline allocation of landing calls, real-time allocation, and then real-time simulation, and that gives us the reality conditions. And I've listed a number of those conditions. What conditions you can start with, which were idealized, and then they become real life. So I've called that progressive introduction of reality. So 3 principles so far. Progressive introduction of reality, where you start introducing reality gradually, and then you're working your way towards the real number. Idealized optimal benchmark tells you what is your hypothetical upper limit, and then random scenario testing allows you to test different results. Let's have a quick look at some results. So, what I've got here, I've got the number of elevators. That's the number of lifts or elevators in the group L. And what this result is trying to show is that as you increase the number of elevators in the group, if you're applying destination, there's actually more and more potential. As you move up here, so as you increase the number of elevators, you're getting more and more potential. The best performing is the IOB, as we expect. And the criteria here is how did we boost? How much is the boost from 100%? That's the benchmark, which is if we do classical conventional control, and how much we boosted. So we can go as high as 200%. We boosted it to around 200% under the IOB. The IOB it can't exist in practice, so in reality we will probably start looking at progressive introduction of reality. As we progressively introduce reality, we go down below and below. When I did this at LFCON, I thought that was the lower limit. You can't go any lower than that. But Richards told me something interesting. He said, you can in fact work to do a very bad allocation. And your allocation can be so bad that you can go below. If you leave it random, that's 100%, that's first come, first served basis. So as passengers arrive under a conventional control system, you just put them all, P passengers in a car and let them go. They don't wait. If you start applying destination, then you start delaying them and putting them organized in cars. But in fact, you can actually make a very bad allocation. You can go below that. We don't want to do that, but it's nice to know that it does exist. So any group control algorithm, destination group control algorithm should be bounded by this triangle. But we know that before actually we've spoken to any manufacturer. Any algorithm in the world, any algorithm you come up with, cannot be outside that triangle. It has to be somewhere inside that triangle. It has to perform there. And anything outside that is not true. So the advantage of the new paradigm, I've looked for the definition of a new paradigm. It's a worldview underlying the theories and methodology of a paradigm. of a particular scientific subject. So it's like a worldview, it's a way of thinking. Every introduction of reality can be assessed independently. And this can be very insightful because we can start thinking about our algorithm, how it affects H and S, because we can see that H and S are quite strong influences. And in fact, what you find is H is actually a much stronger influence than S. If you can reduce H, the highest reversal flow, you would actually have a much bigger effect than changing S or reducing S. The random scenario testing is transparent. The rules are very clear in there. You can see them. I can write them on half a side of an A4. You can read them and agree or disagree with them. And it provides an absolute limit. So you always know that's actually what you're striving for. So we nearly finished. We've got just last 2 slides. I like to end with this cautionary tale of reproducibility. I was fascinated. I had just arrived in England in 1989. I went to see Barney. That was the first shock. The second shock was Fleischmann and Pons. There was a press conference called by Martin Fleischmann and Stanley Pons, University of Utah. And they claimed at the time that they had achieved cold fusion. Fusion at room temperature, which happens in the sun at millions of degrees. And that was obviously an outrageous claim. And they did the experiments and so on, and they called a press conference. Obviously it wasn't true, but it was a very good example of reproducibility, because when they applied for funds from the US government, they sent the report and the experiments for peer review, and not one single scientist could reproduce any of the results. And it was quite an embarrassing situation, but it was a very cautionary tale. And I'll finish with a quotation from, like Alex Salmond, I'm a bit of a closet Trekkie. And I'm just going to do 2 quotations from Captain Jean-Luc Picard. When my wife asks me why we have so little money to spend, I usually quote this: the acquisition of wealth is no longer the driving force in our lives. We work to better ourselves and the rest of humanity. And when she asks me why I'm late and where I am, I say reports of my assimilation are greatly exaggerated. Thank you very much for your attention.